There are many ways to derive the Lorentz transformations utilizing a variety of mathematical tools, spanning from elementary algebra and hyperbolic functions, to linear algebra and group theory. This article provides a few of the easier ones to follow in the context of special relativity. For the simplest case of a Lorentz boost in standard configuration, i.e., two inertial frames moving relative to each other at constant relative velocity less than the speed of light, and using Cartesian coordinates so that the x and x-axes are collinear. Lorentz transformation. In the fundamental branches of modern physics, namely general relativity and its widely applicable subset special relativity, as well as relativistic quantum mechanics and relativistic quantum field theory, the Lorentz transformation is the transformation rule under which all four vectors and tensors containing physical quantities transform. The prime examples of such four vectors are the four-position and four-momentum of a particle, and for fields the electromagnetic tensor and stress-energy tensor. Given the components of the four vectors or tensors in some frame, the transformation rule allows one to determine the altered components of the same four vectors or tensors in another frame, which could be boosted or accelerated, relative to the original frame. A boost should not be conflated with spatial translation, rather it's characterized by the relative velocity between frames. The transformation rule itself depends on the relative motion of the frames. In the simplest case of two inertial frames, the relative velocity between enters the transformation rule. For rotating reference frames or general non-inertial reference frames, more parameters are needed, including the relative velocity, the rotation axis and angle turned through. Historical background. The usual treatment is based on the invariance of the speed of light. However, this is not necessarily the starting point. Indeed, what is really at stake is the locality of interactions. One supposes that the influence that one particle, say, exerts on another cannot be transmitted instantaneously. Hence, there exists a theoretical maximal speed of information transmission which must be invariant. And it turns out that this speed coincides with the speed of light in vacuum. Newton had himself called the idea of action at a distance philosophically absurd, and held that gravity had to be transmitted by some agent according to certain laws. Michelson and Morley in 1887 designed an experiment, employing an interferometer and a half-silvered mirror, that was accurate enough to detect ether flow. The mirror system reflected the light back into the interferometer. If there were an ether drift, it would produce a phase shift and a change in the interference that would be detected. However, no phase shift was ever found. The negative outcome of the Michelson-Morley experiment left the concept of ether undermined. There was consequent perplexity as to why light evidently behaves like a wave, without any detectable medium through which wave activity might propagate. In a 1964 paper, Eric Christopher Zeeman showed that the causality-preserving property, a condition that is weaker in a mathematical sense than the invariance of the speed of light, is enough to assure that the coordinate transformations are the Lorentz transformations. Physical principles assume the second postulate of special relativity, stating the constancy of the speed of light, independent of reference frame, and consider a collection of reference systems moving with respect to each other with constant velocity, i.e., inertial systems, each endowed with its own set of Cartesian coordinates labeling the points, i.e., events of spacetime. To express the invariance of the speed of light in mathematical form, fix two events in spacetime, to be recorded in each reference frame. Let the first event be the emission of a light signal, and the second event be it being absorbed. Pick any reference frame in the collection. In its coordinates, the first event will be assigned coordinates x1, y1, z1, coort1, and the second x2, y2, z2, coort2. The spatial distance between emission and absorption is square root 2 plus 2 plus 2, but this is also the distance c traveled by the signal. One may therefore set up the equation every other coordinate system will record, in its own coordinates, the same equation. This is the immediate mathematical consequence of the invariance of the speed of light. The quantity on the left is called the interval. The interval is for events separated by light signals, the same in all reference frames, and is therefore called invariant. Invariance of interval for the Lorentz transformation to have physical significance. It is crucial that the interval is an invariant measure for any two events, not just for those separated by light signals. To establish this, one considers an infinitesimal interval, as recorded in a system K. Let K be another system, assigning the interval ds2 to the same two infinitesimally separated events. Since if ds2 equals 0, then the interval will be null in any other system, and since ds2 and ds2 are infinitesimals of the same order, they must be proportional to each other. On what may it depend? It may not depend on the two events' position in spacetime. That would violate the postulated homogeneity of spacetime. It might depend on the relative velocity v between k and k, but only on the speed, not the direction, because that would violate the isotropy of spacetime. Now bring in systems k1 and k2. From these it follows. Now one observes that on the right, v12 does not only depend on v1 and v2, but also on the angle between the vectors v1 and v2. The left-hand side does not depend on this angle, and the only way for the equation to hold true is if the function a is a constant, and by the same equation this constant is unity. Thus, for all systems K, and since this holds for all infinitesimal intervals, it holds for all intervals. Most, if not all, derivations of the Lorentz transformations take this for granted, and use the constancy of the speed of light only. This result ensures that the Lorentz transformation is the correct transformation. Standard configuration. The invariant interval can be seen as non-positive definite distance function on spacetime. The set of transformations sought must leave this distance invariant. Due to the reference frame's coordinate system's Cartesian nature, one concludes that, as in the Euclidean case, the possible transformations are made up of translations and rotations, where a slightly broader meaning should be allowed for the term rotation. The interval is quite trivially invariant under translation. For rotations, there are 4 coordinates. Hence there are 6 planes of rotation. 3 of those are rotations in spatial planes. The interval is invariant under ordinary rotations too. It remains to find a rotation in the 3 remaining coordinate planes that leaves the interval invariant. Equivalently, to find a way to assign coordinates so that they coincide with the coordinates corresponding to a moving frame. The general problem is to find a transformation such that to solve the general problem, one may use the knowledge about invariance of the interval of translations and ordinary rotations to assume, without loss of generality, that the frames f and f are aligned in such a way that their coordinate axes all meet at t equals 0 and that the x and x axes are permanently aligned and system f has speed v along the positive x-axis. Call this the standard configuration. It reduces the general problem to finding a transformation such that the standard configuration is used in most examples below. It should be noted that a linear solution of the simpler problem solves the more general problem since coordinate differences then transform the same way. Linearity is often assumed or argued somehow in the literature when this simpler problem is considered. If the solution to the simpler problem is not linear, then it doesn't solve the original problem because of the cross terms appearing when expanding the squares. The solutions. As mentioned, the general problem is solved by translations in spacetime. These do not appear as a solution to the simpler problem posed, while the boosts do. Even more solutions exist if one only insists on invariance of the interval for light-like separated events. These are nonlinear conformal transformations. One has Lorentz transformations, Poincare transformations, conformal group transformations. Some equations of physics are conformal invariant, e.g., the Maxwell's equations in source-free space, but not all. The relevance of the conformal transformations in spacetime is not known at present, but the conformal group in 2 dimensions is highly relevant in conformal fields theory and statistical mechanics. It is thus the Poincare group that is singled out by the postulates of special relativity. It is the presence of Lorentz boosts as opposed to ordinary boosts that separates it from the Galilean group of Galilean relativity. Spatial rotations, spatial and temporal inversions and translations are present in both groups and have the same consequences in both theories. Not all accepted theories respect symmetry under the inversions. Landau and Lifshitz solution. 3 useful hyperbolic function formulae. The problem posed in standard configuration for a boost in the x direction, where the primed coordinates refer to the moving system, is solved by finding a linear solution to the simpler problem, the most general solution, the detailed derivation of which can be found in the section hyperbolic rotation, is, as can be verified by direct substitution using. To find the role of psi in the physical setting, record the origins of f progression, i.e., x equals 0, x equals Vermont. The equations become, now divide, where x equals Vermont was used in the first step, and in the second, which, when plugged back in, gives or. With the usual abbreviations, this calculation is repeated with more detail in section hyperbolic rotation. From physical principles, the problem is usually restricted to 2 dimensions by using a velocity along the x-axis such that the y and z coordinates do not intervene, as described in standard configuration above. The following is similar to that of Einstein. As in the Galilean transformation, the Lorentz transformation is linear since the relative velocity of the reference frames is constant as a vector, otherwise inertial forces would appear. They are called inertial or Galilean reference frames. According to relativity, no Galilean reference frame is privileged. Another condition is that the speed of light must be independent of the reference frame, in practice of the velocity of the light source. Spherical wavefronts of light consider 2 inertial frames of reference O and O, assuming O to be at rest while O is moving with a velocity v with respect to O in the positive x direction. The origins of O and O initially coincide with each other. A light signal is emitted from the common origin and travels as a spherical wavefront. Consider a point P on a spherical wavefront at a distance r and r from the origins of O and O, respectively. According to the second postulate of the special theory of relativity, the speed of light is the same in both frames, so for the point P, the equation of a sphere in frame O is given by for the spherical wavefront that becomes similarly. The equation of a sphere in frame O is given by so the spherical wavefront satisfies the origin O is moving along x-axis. Therefore, x must vary linearly with x and t. Therefore, the transformation has the form for the origin of O, x, and x are given by so, for all t, and thus this simplifies the transformation to where gamma is to be determined. At this point gamma is not necessarily a constant, but is required to reduce to 1 for Vc. The inverse transformation is the same except that the sign of E is reversed. The above 2 equations give the relation between t and t, as, or replacing x, y, z, and t, in the spherical wavefront equation in the O frame, with their expressions in terms of x, y, z and t produces, and therefore, which implies, or comparing the coefficient of T2 in the above equation with the coefficient of T2 in the spherical wavefront equation for frame O produces. Equivalent expressions for gamma can be obtained by matching the x2 coefficients or setting the tx coefficient to 0. rearranging, or choosing the positive route to ensure that the x and x-axis and the time axis point in the same direction, which is called the Lorentz factor. This produces the Lorentz transformation from the above expression. It is given by the Lorentz transformation is not the only transformation leaving invariant the shape of spherical waves, as there is a wider set of spherical wave transformations in the context of conformal geometry, leaving invariant the expression. However, scale-changing conformal transformations cannot be used to symmetrically describe all laws of nature including mechanics, whereas the Lorentz transformations represent a symmetry of all laws of nature and reduced to Galilean transformations at Galilean and Einstein's relativity. Galilean reference frames in classical kinematics. The total displacement x in the R frame is the sum of the relative displacement x in frame R, and of the distance between the two origins x minus x. If v is the relative velocity of R relative to R, the transformation is x equals x plus Vermont, or x equals x minus Vermont. This relationship is linear for a constant v, that is when R and R are Galilean frames of reference. In Einstein's relativity, the main difference from Galilean relativity is that space and time coordinates are intertwined, and in different inertial frames tt. Since space is assumed to be homogeneous, the transformation must be linear. The most general linear relationship is obtained with four constant coefficients, a, b, gamma, and b. The Lorentz transformation becomes the Galilean transformation when gamma equals b equals 1, b equals minus v and a equals 0. An object at rest in the R frame at position x equals 0 moves with constant velocity v in the R frame. Hence, the transformation must yield x equals 0 if x equals Vermont. Therefore, b equals minus gamma v in the first equation is written as principle of relativity according to the principle of relativity. There is no privileged Galilean frame of reference. Therefore, the inverse transformation for the position from frame R to frame R should have the same form as the original but with the velocity in the opposite direction, IOW, replacing v with v, and thus the speed of light is constant since the speed of light is the same in all frames of reference. For the case of a light signal, the transformation must guarantee that t equals x, c when t equals x, c. Substituting for t and t in the preceding equations gives. Multiplying these two equations together gives, at any time after t equals 0, x is not 0. So dividing both sides of the equation by x results in which is called the Lorentz factor. When the transformation equations are required to satisfy the light signal equations in the form x equals quart and x equals quart, by substituting the x and x values, the same technique produces the same expression for the Lorentz factor. Transformation of time. The transformation equation for time can be easily obtained by considering the special case of a light signal, satisfying substituting term by term into the earlier obtained equation for the spatial coordinate gives so that which determines the transformation. Coefficients a and b are so a and b are the unique coefficients necessary to preserve the constancy of the speed of light in the primed system of coordinates. Einstein's popular derivation. In his popular book, Einstein derived the Lorentz transformation by arguing that there must be two non-zero coupling constants lambda and mu such that correspond to light traveling along the positive and negative x-axis, respectively. For light x equals quart if and only if x equals quart. Adding and subtracting the two equations and defining gives substituting x equals 0 corresponding to x equals Vermont and noting that the relative velocity is v equals bc, gamma. This gives the constant gamma can be evaluated by demanding c2t2 minus x2 equals c2t2 minus x2 as per standard configuration. Hyperbolic rotation. The Lorentz transformations can also be derived by simple application of the special relativity postulates and using hyperbolic identities. Relativity postulates start from the equations of the spherical wavefront of a light pulse, centered at the origin, which take the same form in both frames because of the special relativity postulates. Next, consider relative motion along the x-axis of each frame, in standard configuration above, so that y equals y, z equals z, which simplifies to linearity. Now assume that the transformations take the linear form, where a, b, c, d are to be found. If they were nonlinear, they would not take the same form for all observers, since fictitious forces would occur in one frame even if the velocity was constant in another, which is inconsistent with inertial frame transformations. Substituting into the previous result, and comparing coefficients of x2, t2, xt. Hyperbolic rotation. The formulae resemble the hyperbolic identity. Introducing the rapidity parameter as a parametric hyperbolic angle allows the self-consistent identifications where the signs after the square roots are chosen so that x and t increase. The hyperbolic transformations have been solved for. If the signs were chosen differently, the position and time coordinates would need to be replaced by -x and or -t so that x and t increase not decrease. To find how relates to the relative velocity. From the standard configuration, the origin of the primed frame x equals 0 is measured in the unprimed frame to be x equals Vermont.